at Technical University of Denmark. And the role of DTU is to provide the computational support for the development of magnesium batteries. So I will present the overview of our activity that we did during this month. So I'm going to skip the introduction to magnesium batteries because we heard a lot about this already. But at DTU, we are focused on the development of materials for all three parts of the batteries. And we can set some goals to all of these materials. But in general, when we think about batteries, the new batteries, we want them to be safe, to have a high capacity, and to provide a high difference in the voltage. So if you are thinking about the calculations, we can help in the development of materials in two ways, by doing calculation for many different materials and try to screen and propose some new materials, or trying to provide some understanding and explanation of the properties that we already seen, and then go to more rational design of the materials. So during the presentation, I'm going to show you 4 examples of the support from the calculations on the cathode side, electrolyte side. And also, if you are interested in anode, please stay to the talk of Smolny Vincent, that is a PhD student at DTU, and is working on the anode side. So starting with the cathode, our main task is to provide some materials to say which materials should have the best properties for being the cathodes in the magnesium batteries. And to do that, we are going to study hundreds of materials, and that's a lot. So to do that manually, to do calculation manually, is quite complicated. And to do that, our colleagues here, Felix and Ivano, already established the autonomous procedure for calculating, and it minimizes the interaction of human with a computer. So basically, it's some kind of script, some kind of program that do everything instead of us. The human interaction is just we need to prepare inputs, so list of the materials that we want to screen, and then make decision a few steps. So at the beginning, the script is calculating the stability of the material. Then we calculate the potential, electrochemical potential of the material. And at the last step, we are calculating the properties about diffusion. So as we can see, we are going from the properties that are very easy to calculate to more advanced. And thanks to that, at each of the decision step, we can decide if some of the materials already don't have a properties that we want, so we can just skip them and do the more advanced calculation only to the materials that are the most promising. And thanks to that, we are saving computational time, and we can screen more materials. So the most important in that is that we are looking both at thermodynamics and kinetics. And in case of magnesium batteries, it's very important because magnesium very often gets stuck in the structure. So we can have a material that will have a very high potential, but then we cannot remove magnesium at all. So this cathode doesn't work. So if you will do entire procedure, at the end, we will have properties like volume change, stability of material, and also potential and energetic barrier at different state of the charge of the batteries. And based on that, we can say which material should behave good in experiments. So we already did the studies, the screening for over the 100 structures from ICSD database. And based on that, we are able to indicate some new materials that can be promising. And our studies indicated these 2 materials with quite good properties, with high potential. Maybe energetic barrier is a bit still high, but for other one, we have a bit lower potential, but very, very low energetic barrier. And indeed, these materials were as input to our experimental partner in Barcelona, the group of Professor Rosa Palazzini, where this material were already synthesized, and they are undergoing the experimental tests now. So moving to another part of the work that we are doing on cathodes is vanadium pentasulfide. And here you already heard about this material yesterday, because we are collaborating here with KIT. So Jenny was presenting experimental results yesterday and showed that this material has very specific electronic structure. We see the bonding, anti-bonding orbitals here from S22 minus ligands that are the structure is completely collapsing when we add in more electrons. And also the flexibility of the structure provides a very good diffusion path. Okay. So you can see that thanks to the structure, the energetic barrier is lower. We can see that, okay, the energetic barrier is still high for this case, but we are doing calculation just for one magnesium in the structure. So if you want to see what really is happening in the material, we need to look what is happening when we are charging completely material. So we were doing this, just putting magnesium atoms in random places, trying to find the most optimal place where magnesium will sit. And we are doing this for many random configuration to find out which structure will be the most stable. And here I'm presenting the structures that got the lowest energy. And what is interesting here is that if you look, when we put extra magnesium to the structure, it always goes to the place close to magnesium already. So the magnesium is not uniformly located in the entire cell. It's always just close to each other. And then if we look at the energies, so I should mention here that each of the dots, green, blue dot, represent one structure and one energy that we got. So in fact, we are interested just in the lowest energies, so the lowest dots. So if we look closely into that, we can see that for the structure with magnesium, from 1 magnesium to 5 magnesium in the structure, we have energies that are indicating not stability of the phase. That means we have a phase that has, for example, 3 magnesium in the structure, which will decompose, disproportionate to the empty one, and the one with 6 magnesium. That means this material have a very specific charging mechanism that at the beginning is heterogeneous, and then when we reach the phase that is stable, we are able to charge it homogeneously, so charging 1 magnesium by 1. So because of that, when we look at simulated OCV, we should have a plateau and then potential that is slowly dropping. And indeed, if you compare that with the experimental results from KIT for the first cycle, we can see that at the beginning we are seeing plateau and then it's decreasing. So we did calculation up to concentration equal 1. So if you see here, we have a quite good agreement also with potential that is close to 1, and here is 1. But what is interesting is what is happening here. So this is still undergoing because it's a very difficult region of the cathode, and you are trying to find what is the structure there, how it does it impact the kinetics, and what is the degradation mechanism, because we can see that after going here, the cathode behave completely different way. And so far, what we see in the calculations is that the bond between vanadium and sulfur is very weak when there is a lot of magnesium close by. So probably we will observe the formation of MGS inside the cathode, and probably this is the degradation mechanism that is causing the complete change of the shape of the curve. So switching now to electrolytes, so far the requirements for the electrolytes are that electrolytes should be readily stable with a metallic anode, so to prevent any formation of passivation film that could prevent the ionic transfer between electrolyte and magnesium. So because of that, we are using usually low polar solvents, and that together with double charge of cation causes huge aggregation of the system and formation of clusters. And indeed, these clusters are responsible for most of the properties of electrolyte. So if we want to study the change of the solvent or salt and look how is the impact on the electrolyte properties, we need to find out what is the structure of these complexes. So indeed, in DTU, we are trying also to suggest some other solvents or change of the salt. So at the beginning, with going to the solvent, we did just simple screening, just looking at interaction energy in a vacuum between magnesium and different solvents, different group of solvents. And what we notice is that from the solvent that we screen, only ethers providing like middle strength of the interaction. So only these solvents will provide easier desolvation. So we went in more details into the glimes. And here, first, we noticed that in the community, usually it's used, community usually use THF or monoglyme because the solvents are quite simple, creating simple structure that you can easily determine even if XRD. They give a high dynamic, low viscosity, but the problem with them is that they have also high volatility because the boiling point is quite low. So that means if your battery will start to heat up, there could be a very dangerous situation. So what we wanted to do is to switch to some other glimes, longer glimes, extend the chain. And thanks to that, we can avoid the low boiling point, so have lower volatility. But the problem here is that the structure is quite complicated of the complexes and the desolvation mechanisms also. But we wanted to study this. What we want to do to see how the change of the solvent will impact the electrolyte performance. So for that, we just took the simplest system as we can imagine. So just chlorine atom, chlorine anion. And this system we have a simple anion. It's the most common system, and a calculation for that can represent many different types of the electrolytes. And inside this electrolyte, electroactive species are created by the reaction between this reagent. And as a result, we are usually getting monomagnesium clusters like that, or some more complicated multi-magnesium clusters. So to understand everything, we need to look both at the formation of monomagnesium and multi-magnesium clusters. So going to monomagnesium clusters is quite easy. These clusters are quite simple. To study them, to find out what is the structure, we just need to look at the energies when we add more oxygen atoms close to the magnesium, and then observe when we will see the minimum energy that represents the most thermodynamically stable state. So we can do it for many different solvents and for many different structures with one chlorine and two chlorines. And we can see that for most of them, the coordination number 6 is preferred, but for longer lines, suddenly also 7 is a little more stable. That can be quite surprising because magnesium would expect that it always will be coordination number 6 or maybe even lower. But indeed, when you look at the literature, there are already some reports about the coordination number 7 for magnesium. And this is for magnesium TFSI in tetraglyme, when magnesium is coordinated by the 5 oxygens from the tetraglyme and then 2 anions. And that's just because of the super strong halating effect of these glymes. So then we wanted to go also to more advanced systems, so with multi-magnesium. And these multi-magnesium clusters can be seen as a result of reaction of these simple clusters together with MgCl2, with a salt, and creating the dimers, so clusters with 2 magnesium or even 3. We could go also further, but DFT calculation getting very, very expensive if we include much more magnesium. So we have to stop here. But what we can say here is that if you go further, even here we have a lot of topologies, how the atoms are arranged, and that we need to test all of the examples to know which one is really the one that is providing the lowest energy. So, for example, if we look at this Mg2Cl3, we have a 3-2 possibility. One is the pyramidal, when you have 2 magnesium here and here, and 3 chlorines that are shared between this magnesium. And also it can be like we have a linear one, when with 1 chlorine that is shared between 2 magnesium and 2 chlorines that are just separated onto 1 magnesium. And if we just do the calculation, trying to put there also solvent, weighting the magnesium, we can see that the lowest energy structure we get for THF only if we consider these pyramidal structures, because THF has a more bulky structure. So it prefers that magnesium will be coordinated also from a lot of chlorines. If you look at the glimes, they have a more halide system characteristics. So it's they want to make some kind of disk around magnesium, and that limits access to the magnesium from chlorine, and that's why they are preferring linear one. But what's interesting here, if you look at D-glime is behaving quite different. It's also like creating linear structures, but they are more condensed and going more into direction of this more aggregated. So we can do that for all of the clusters. And here I'm showing just the summary of this analysis. So showing only the most stable structures that we found in a schematic way. So the energies are showing the formation energy calculated per one magnesium. And what is important here, I should mention at the beginning, is that when you want to compare the energies between clusters that have a single charge and double charge, we need to, so we have a release of chlorine, and this chlorine is usually reacting in the electron with another components, like here, for example, LaCl3, and that reaction also need to be included if we decide if some cluster is more stable or less stable. So for LaCl3, the energy the correction that need to be included is around 26 kilojoule per mole, and for others we estimate it's like 20-30 kilojoules per mole. So if you look at this only for monoglyme, the differences are very small, and double charge cluster will be stabilized like this. What's other interesting, if we are comparing tetraglyme with triglyme, we can see that the structures are very similar. These two solvents are almost providing almost the same clusters. So the fifth oxygen from the tetraglyme is just stabilizing the cluster, but doesn't really change the nature of the solvent. Also, what we can see is that there is huge similarity between monoglyme and triglyme. So usually the structure is like, if you take two monoglymes, it's represent one triglyme. Only D-glyme is behaving quite different, because if you can see here, for example, the one D-glyme is shared between two magnesiums that makes them much closer and the structure much more condensed. And here, even the structure is really aggregated because of that. So what is happening here? D-glyme has just 3 oxygens, and this apparently is too little for fully solvate magnesium, but it's too much to use 2 molecules of D-glyme just to solvate. The solvatation shell will be too crowded if you are using 2 molecules. So the system is just evolving to more concentrated systems, to more concentrated clusters, creating things like that. But the most important is to see what is the connection between these structures that we generated, that we think they are most stable for the electrode process. And at the electrode, we have 2 processes that are happening. And so we have the solvation and reduction. These 2 processes are overlapping on each other, but in calculations, it's very difficult to make it like in the same time. We can do calculation for desolvation, just removing magnesium, and also doing the calculation for reduction, adding 1 electron to the system. And when you compare these results with the clusters that we created, we see that increase in cluster size have a positive impact on desolvation, because it's easier to remove magnesium when there is also another magnesium in the structure, but it has a bad impact on the reduction. The good impact was found if we have chlorine that are bridging in the structure, so they are connecting 2 magnesiums. because in that case, the electron density that is shared from chlorine to both magnesium can be easily shifted from one to another in case of we remove one magnesium or we reduce one of the magnesium. And a high solvent content is also have positive effect on the desolvation, because if you have more content of solvent, it's the interaction between magnesium and chlorine are getting weaker. So because of that, it's much easier to remove it. So based on that, we can see why THF is working so good, because it induces the best clusters that we can see. But if you want to go to some other solvent that is less volatile, dig lime is just the best candidate among the limes. I have also the fourth part of the presentation, but I can see that I don't have time. Luis?
Yes, just a couple of minutes more. Go ahead.
Okay. So we are also trying to find some new anions, because we know that chlorine are not good because they are causing corrosion of the battery. So we want to find some anions. So in the project, we are using the salt that we've developed in KIT, and we just want to see why the salt works so good. So first of all, we went through the literature, just studying different anions salts that were reported to provide a good plating stripping, calculate for them the interaction energy. We see that for boron 1, it's really the interaction energy is quite small, but also for others, like the interaction energy can be higher and it's possible to plate. So it's not the most important. We were trying also to look at the stability, calculating electron affinity and ionization potential, calculating this also for TFSI, that we know that it really doesn't work, TFSI. So to try to see the difference, we also relax the structure, calculate reduction potential, oxidation potential, but we cannot see anything like indicating. So we went through many different descriptors that can find us. And finally, we found that the bond dissociation energy in the reduced form of this cluster can serve as a very good indicator if the salt will provide us reversible plating stripping. So you can see for all of them, you have a positive value, and only for TFSI, there is negative value. And why this descriptor works? Probably because when we reduce magnesium, we are going through, and we want to plate, we are going through this metastable magnesium plus state. And we want, of course, to reduce it more, add more electrons. But what can happen is just this super reactive species will react with anion, and we will see the decomposition product. So what we want to stop that. So we need to design the anions in the way that they will provide the stability against this electron. So what we try to do is just to look at this anion and see if we put other ligands there, what will happen. So we did calculation for reduction potential, oxidation potential, and also for dissociation for the first anion and second anion. And based on that, we can select some ligands that should be promising just based on that, with a high oxidation and low dissociation energy. And then going to the composition, we found out that this mechanism of breaking this bond and this bond is the weakest point of the salt when we add this magnesium plus. So we studied this for all of the ligands and find out that there is quite clear connection between the structure and the stability, because if we have a lot of groups connected here to this carbon, it will stabilize the radical form here. And if we have a lot of withdrawing groups like CF3, we will have stabilization of this species. And all of these effects are just moving the reaction in this way, making it easier to break the structure. So we need to, when we design an ion, we need to find the balance between this withdrawing of the electrons due to that we want to have low dissociation energy, and this not too high withdrawing because we will lower the stability. So if we look at the structures selected on the previous slide, and with the one that here calculations are showing that we have a stability. We can see this tree, and indeed this is the one that is extensively studied in our project. So here I have a conclusion to each of the parts. So I think I don't have time. So I just hope I managed to show you that DFT calculation can be really useful for development of battery and materials, both by screening this and or providing some understanding of already seen results. And at the end, I just want to thank all of the group of DTU who is working on eMagic, and also two experimental group that we are collaborating the most in the eMagic project. And thank you.
Thank you, Pierre, for this nice talk. So far, I don't have any Q&A here written from the audience. Let's see, probably one, Gian Sebastian Filo, who is thank you for the nice presentation.